Swayam Prabha. Digital India. Educated India.
So, in continuation of permutation, we have permutation with repetition. So, in this topic, we have to discuss some examples in how many strings of length r can be formed from the uppercase letters of the English alphabet. Now, the solution to this problem is by the product rule. There are 26 uppercase letters. So, and because each letter can be used repeatedly, we see that there are 26 power r strings of uppercase letter of the letters r and length r. So, this is a way we can do for the string of length r can be formed of the uppercase letter of the English alphabet. Now, keep it in mind this example. Let us go with the statement of the theorem. The number of r permutation of a set of n objects with the repetition allowed is n power r, that we have to prove. The proof is there are n ways to select an element of the set for which r position in the r permutation when the repetition is allowed, because each choice of n objects are available. Hence, by product rule there are n power r permutation when repetition is allowed. So, this way we can start with the proof of theorem 1. Now, we will discuss one example. How many ways are there to select the 4 pieces of the fruit from a bowl containing apples, orange and pears? If the order in which the pieces are selected does not matter, only the type of a fruit and not in the individual piece matters, that there are at least 4 pieces of each type of the fruit in the bowl. So, this is a problem. Now, let us discuss deeply to solve this problem. We have a list all the way possible to select the fruit. There are 15 ways of 4 apples, 4 orange, 4 pears, right, and 4 apples can do for 3 apples and 1 orange, and 4 oranges can be do with 3 apples and 1 pears, and 4 pears can arrange in 3 oranges and 1 apple, and in this way go 3 oranges and 1 pear corresponding to 4 apples, and corresponding to 4 apples further we can do 2 apples and 2 oranges, and then further we can divide into 2 possible way of combination is 2 apples, 1 orange and 1 pear. Similarly, for 4 oranges, 3 apple and 1 pear, and 3 pears 1 apple, and 2 apples and 2 pears, 2 oranges 1 apple and 1 pear, and for 4 pears 3 oranges and 1 apple, and 3 pears 1 orange, 2 oranges 2 pears, 2 pears 1 apple and 1 oranges. So, this is a way we can do for the combination. The solution of the number of 4 combination with the repetition allowed from 3 element set are like this, the 4 of apple, orange and pear. Now, another theorem based on that theorem 1, if you have a n plus r minus 1 c r can be written as n plus r minus 1 c n minus 1 or combination from a set with n element when repetition of the elements is allowed. Now, we have an example. Suppose that a cookie shop has 4 different kinds of cookies. How many different ways can 6 cookies be chosen? Assume that only the types of the cookie and not the individual cookies or the order in which they are chosen matters. The solution is The number of ways to choose 6 cookies is the number of 6 combination of a set with 4 elements. From the above theorem says that what n equal to 4 and r equal to 6, and then we have n plus r minus 1 can be written as 4 plus 6 minus 1 comma 6 combination, which is equal to what 9C6, because 9C6 is equal to 9C3, which is equal to 9 into 8 into 7 by 1 into 2 into 3 equal to 84. There are 84 different ways to choose the 6 cookies. Now we have another example. How many solution does the equation x1 plus x2 plus x3 equal to 11 have, where x1, x2, x3 are non-negative integers? See, it is infinitely many solution of Diophant equation, but we have to do with the help of the combination how we can discuss. Now, to count the number of solution, we note that solution corresponding a way of selecting 11 items from a set where 3 elements, so that x1 item of the type 1, x2 item of the second type 2 and x3 items of the type 3 are chosen. Therefore, the number of solution is equal to the number of 11 combination with repetition allowed from a set with 3 elements. Therefore, from the theorem it follows that 11 plus 3 minus 1 C11 equal to 13 C11, which is equal to 13 C2, which is equal to what 13 into 12 divided by 1 into 2, which is equal to 78. So, this way we can do for finding the solution to the problem. Now, in continuation of the above problem, we have possibilities of the number of solution of x1 and x2, x3 based on the condition that x1 greater than equal to 1 or x2 greater than equal to 2 or x3 greater than equal to 3, and then the solution of this can be found by subject to the constraint, and then these constraints are corresponding selection of 11 items with x1 terms of the type 1, x2 terms of the type 2 and x3 terms of the type 3. In addition, there is at least one item of the type 1, 2 item of the type 2 and the 3 item of the type 3. So, a solution corresponding to the choice of one item of the type 1, 2 or of type 2 and 3 of type 3 together with the choice of live additional items of the type. Therefore, by theorem this can be done with the help of what n 3 plus 5 minus 1 C5 is equal to 7 C5, which is equal to 7 C2, because NCR equal to NC n minus R. So, this term will come like that. Therefore, it becomes 7 into 6 by 1 into 2 equal to 21 ways. Thus, there are 21 solution of this equation subject to the given constraints. So, based on this condition of the constraint, we can get the possible solution to the problem. Next, without repetition, this is a general formula for without repetition of combination and permutation, and with and without repetition, what is the corresponding formula. Now, the type is R permutation, the repetition allowed is no, therefore, corresponding formula is n factorial by n minus R factorial. For the type of R combination, repetition allowed is no, then the corresponding formula is n factorial by R factorial into n minus R factorial. The type of R permutation, repetition allowed is yes, and then the resultant is n power R. For R combination, the repetition allowed is yes, therefore, it becomes n plus R minus 1 factorial by r factorial into n minus 1 factorial. So, this is the general formula for permutation combination with and without repetition. Now, we have a problem. What is the value of k after the following pseudo code has been executed? Value of k starts with 0 and for I1 equal to 1 to n, for I2 equal to 1 to I1 and so on, for Im equal to 1 to Im minus 1 and k equal to k plus 1. So, the solution is the initial value of k is 0 and 1 is added to k, and each time the nested loop is traversed with the sequence of integer I1, I2 and so on Im, such that 1 is less than or equal to Im, less than or equal to Im minus 1 and so on, I1 less than or equal to n. Therefore, number of such sequences of integer is number of ways to choose m integer from 1 to n with repetition allowed. To see this, note that once such a sequence has been selected, if we order the integer in the sequence of non-decreasing order, this uniquely defines the assignment of Im, Im minus 1 and so on I1. So, conversely, every such assignment corresponds to a unique unordered set. Hence, from the theorem it follows that k equal to n plus m minus 1 C m after this code has been executed. So, this is a way with the help of the combination ideas how we can execute the value. Now, next idea is permutation with an indistinguishable object. Some elements may be indistinguishable in counting problems. When this is the case, care must be taken avoid to counting the things more than once. So, consider the example 7. How many different strings can be made by reordering the letters of the word success? Because some of the letters success are the same. The answer is not given by the number of permutation of the 7 letters. This word contains 3 S, 2 C's and 1 U and 1 E. So, to determine the number of different strings that can be made by reordering the letters, first note that the 3 S can place among the 7 position is 7C3 different ways, and leaving 4 position free, then the 2 C's can be placed in 4C2 ways, and leaving the 2 free position, the U can be placed in 2C1 ways, leaving just one position free. Hence, E can be placed in 1C1 way. Consequently, from the product rule, the number of different strings that can be made is 7C3, 4C2, 2C1 and 1C1, which is equal to 7 factorial by 3 factorial into 4 factorial, 4 factorial by 2 factorial into 2 factorial, and 2 factorial by 1 factorial into 1 factorial, and 1 factorial by 0 factorial into 1 factorial, which is equal to what? The resultant is, so cancel these two, right. So, that 7 factorial by 3 factorial into 2 factorial into 1 factorial into 1 factorial, which is equal to what? 3 factorial into 4 into 5 into 6 into 7 by, so 3 factorial into 2 factorial into 1. Therefore, cancel these two, so that the resultant is 420. Now, this way we can find the value of what this problem. Now, we have to do one theorem based on indistinguishable object. The number of different permutation of n objects where there are n1 indistinguishable object of the type 1, n2 indistinguishable object of type 2 and so on, nk indistinguishable object of type k is n factorial by n1 factorial into n2 factorial and so on nk factorial. So, proof: to determine the number of permutation, first note that n1 object of the type can be placed among the n position is nc1 base, and leaving n minus 1 position free, then the object of type 2 can be placed in n minus n1 c n2 base, and leaving n minus n1 minus n2 position free, continue the placing the object of the type 3 and so on the type k minus 1 until the last stage nk object of the type k can be placed in what, n minus of n1 plus n2 and so on n minus k comma nk, or n minus n1 minus n2 and so on minus n minus k minus 1 comma nk base. Hence, the product rule, the total number of different permutation is nc n1, n minus n1 c n2 and so on, n minus n1 minus n2 and so on n minus k minus 1 c nk. So, the meaning is n factorial by n1 factorial into n minus n1 factorial into n2 factorial into n minus n1 minus n2 factorial and so on nk factorial into 0 factorial. So, corresponding this one we can write like this. Therefore, we have what, cancelling this like that it goes, we have the resultant is n factorial by what, n1 factorial, n2 factorial and so on nk factorial. So, this is the required resultant of the given question. Next one is distinguishable object and distinguishable boxes. For example, how many ways are there to distribute hands of 5 cards to each of 4 players from the standard of 52 cards? So, this is the meaning of distinguishable object and distinguishable boxes, right. So, here we have to discuss the problem, apply with the help of the product rule, and to begin note that the first player can be dealt 5 cards in 52 C5 ways, the second player can be dealt with 5 cards in 47 C5 ways because only 47 cards are left. The third player can be dealt 5 cards in 42 C5 ways. Finally, the fourth player can be dealt 5 cards in 37 C5 ways. Hence, the total number of ways to deal the 4 players 5 cards each is 52 C5, 47 C5 into 42 C5 into 37 C5. So, which is equal to 52 factorial by 47 factorial into 5 factorial, and then 47 factorial by 42 factorial into 5 factorial, and then 42 factorial by 37 factorial into 5 factorial, and then 37 factorial by 32 factorial into 5 factorial. So, the resultant is what? So, 52 factorial by 4 times of 5 factorial into 32 factorial. So, this way we have a solution of distinguishable object and distinguishable boxes. Next, indistinguishable object and distinguishable boxes. How many ways are there to place 10 indistinguishable balls into 8 distinguishable bins? So, the number of ways to place 10 distinguishable balls into 8 bins equals the number of 10 combinations from a set with 8 elements when repetition is allowed. Consequently, there are 8 plus 10, right. Here n equal to 10, r equal to 8 and minus 1 equal to comma 10. So, that it becomes 17 C 10, which is equal to what? 18 minus 1 equal to 17, 17 C 10 into 17 factorial by 10 factorial into 7 factorial, which is equal to 19,448. So, this way we can find the what? Indistinguishable and distinguishable boxes. Next, distinguishable object and indistinguishable boxes. How many ways are there to put 4 different employees into 3 indistinguishable offices when each office can contain any number of employees? So, we will solve this problem by enumerating all the ways these employees can be placed into offices. So, we represent the 4 employees by A, B, C, D, right. First, we note that we can distribute employees so that all the 4 are put into one of the offices and 3 are put into one office and 4 are put into second office and 2 employees are put into one office and 2 put into second office, and finally, the 2 are put into one office and 1 each put into other 2 offices. So, keep it in mind this. So, this way to distribute these employees to these offices can be represented by the way of partition element of A, B, C and D into disjoint subsets. So, we can put all the 4 employees into one office is exactly one way, represented by A, B, C, D. And also we can put 3 employees into one office and a fourth employee into different office is exactly 4 ways, that is A, B, C, D 1, A, B, D comma C and A, C, D comma B and B, C, D comma A. We can put 2 employees into one office and 2 into second office is exactly 3 ways, that is A, B, C, D, A, C, B, D and A, D, B, C. So, finally, we can put 2 employees into one office, the one each into each of the remaining 2 offices in 6 ways, represented by A, B, C, D, A, C, B, D, A, D, B, C, B, C, A, D, B, D, A, C, C, D, A, B. So, this way we can split it into distinguishable object and indistinguishable boxes. Therefore, we can count all the possibilities. We find there are 14 ways to put 4 different employees into 3 indistinguishable offices, and another way this problem is to look at the number of offices into which we put employees. So, note that there are 6 ways to put 4 different employees into 3 indistinguishable offices, so that no office is empty. So, 7 ways to put 4 different employees into 2 indistinguishable office, so that the no office is empty, and 1 way to put 4 employees into one office, so that it is not empty. So, this way we can complete the indistinguishable object and indistinguishable boxes. Next one is indistinguishable object and indistinguishable boxes. Then we will discuss one example. How many ways are there to pack 6 copies of the same book into 4 identical boxes, where the box can contain as many as 6 boxes? So, we will enumerate all ways to pack the books, for which the pack of the books will be listed in the following different pack of the boxes, and then with the largest number of books followed by the members of books in each box containing at least one book. In order of decreasing number of books in a box, the ways we can pack the box are: one way is 6, another way is 5 comma 1, another way 4 and 2, another 4 1 1, 3 3, 3 2 1, 3 1 1 1, 2 2 2 and 2 2 1 1. So, for example, 411 indicates that one box containing 4 books, second box containing a single book, and third box containing single book, and the fourth box is empty. So, this way we conclude that there are 9 allowable ways to pack the books, because we have all listed above, and this is the possibilities of what combination, right. So, this is indistributable and indistributable boxes.